Okay, so this is the CHEM3120 Organic 2 Exam 2 review slides for spring of 2016 with that. So we're going to go over the free answer part of this. So okay, so you're going to get a series of reactions. You got to tell me which kind of, predict the mechanism on these things, if it's going to be a substitution reaction or an elimination reaction, and what type, like that. So here we go. So right, so for this one, right, we're substituting the bromine for the iodine here. So it's a substitution, so it's going to be one of the SN1, SN2 reactions, right? But then you have to say which one is it going to be, right? So for SN1, right, they like to have primary, the leaving group on the primary carbon, like that. So because you're coming in there and you need to deal with the, you not have any sterics around, so like that. But for tertiary ones, right, or for SN2, they like tertiary carbons, right? So here your carbon's attached to this, the bromine's attached to this carbon, and there's 1, 2, 3 other carbons attached to it, right? So that makes this tertiary, which SN1 likes tertiary carbocations, right? So this is an SN1 reaction, right? So you need to look to say, okay, where's substitution? Is it on a primary, secondary, or tertiary carbon, right? Is that where's the leaving group? Since this one's on a tertiary, SN1 likes the tertiary carbon, so it's going to be an SN1 reaction. Okay. Now for this one, all right. So with that, so see how we're making this double bond here. So it's going to be one of the elimination products, right? So it's really hard to tell between E1 or E2, and actually I'll accept either ones for these products. But we do have to take into account if it's this E1CB mechanism. When it is, what you're going to see is this: it's the double bonds in conjugation. So you have a double. The product formed is always going to have this double, single on down the road, sort of pattern here. So here we go. So here you have a double, single, double, like this, double, single, double. Right? So there's a double bond here, single bond, double bond, like that. Whenever you see that double, single, double, it's going to be this E1CB mechanism. How about that? So now for down here, it's a very similar product here, but what do we have? We have a double, single, single, double. We don't have this pattern of double, single on down the road, right? So it's going to be like this. So the right. So I'll either take E1 or E2, right? They're going to give the same product, right? So you would need a lot more information and need to know the mechanism and everything else like that, which in order to be able to tell if it's E1 or E2. So I'll take either one. So with that, okay, so there's going to be some predict the product questions on here. All right, so with that, so for here, right, so with that, so I'm going to tell you what the reaction is, right, and you're going to have to tell me, as well as the type of mechanism we're going to be using for this, if it's E1 or if it's an SN1, SN2, whatever. All right, so with that, so I'm going to give you the information about the reaction conditions. Okay, and so in order for there to be an E2, right, we're going to need to make a double bond. So you need to have 2 carbons to play with this, right? So you need to be able to rip off one of the hydrogens on one side, right? And you have a leaving group on the other, right? So this is a CH3 on this group, right? So we could make a double bond there. There's also a CH2 on this group, right? So there's a hydrogen on this carbon here, so we could make a double bond there. Okay, so if we make this one here, put the double bond there, right? There's a hydrogen here, hydrogen there, right? Or we can make a double bond there, right? With that, so there. So now it's a CH2, right? Because we ripped off one of those hydrogens, right? So with that, so and that there was always a hydrogen there, right? So there was always a hydrogen there. This hydrogen that's remaining. Now those are the 2 products. Okay. Now we need to figure out which one's the major product. In order to do that, you need to figure out how many hydrogens are hanging off of this, directly off this double bond. Okay, not about that. So technically, the idea is how substituted is it, but an easy way of doing it is looking at the hydrogens, right? So for this one, right, there's 2 hydrogens hanging off of it. Here, there's these 2, and this one, right? So there's 3 hydrogens hanging off of it. You want as few of hydrogens as possible, right? So that makes this one the major product. Okay, so I want to see both of them, and I want you to tell me which one's the major product. Okay, same thing happens down here, but for the cyclohexanes, what you need to do is you need to be able to put the the leaving group, in this case bromine, in an axial position, and then what you need is another hydrogen in an axial position next to it. Okay, so you need to have leaving group. So this one we're going to need a hydrogen in the axial position. This one we're going to need a hydrogen in the axial position, right? So there's a hydrogen here, right? And then there's two hydrogens there and there. Okay, so in order for this to get into axial, right, we need to do a chair flip, right? So that puts it, right? So we'll label these, right? We'll label these 1, 2, 3, 4, 5, 6, just so you can sort of see. It's a little bit easier to keep track of where things are. So you keep these sort of middle ones, these middle carbons the same, and you just basically flip that guy, the one that's down, flip that up. Take the one that's up, flip it down. Okay, so if I want to label these, this would be 1, 2, 3, 4, 5, 6, right? So this hydrogen, right? So the bromine, which was on 6, right? So before there was a right? The bonds point towards the axial, right? So there's a hydrogen axial up, so that becomes equatorial, right? And now the bromine becomes axial, right? Because you always flip axial and equatorial. Like this here. On carbon 1 here, right, there's the methyl group is equatorial, so now it becomes axial. That means the hydrogen is equatorial. Here there's just two hydrogens, right, so they go like that. So here, right, so here's an axial bromine, here's an axial hydrogen, right, so we can make a double bond here. Okay, now you would normally think, oh, well, there's a hydrogen here, right, that would be fine, but the problem is it's really this methyl group here that's axial. We would need to get that hydrogen axial in order to be able to react here. So there's actually no way that we can put a double bond here. So there's actually really only one product. It's just this. That right there. Right, we can't put a double bond here, right, because this methyl is in the axial position. What we would need to have is the hydrogen axial. Here, notice how this one's axial and then this hydrogen is axial, so we're good to go between the 5 and the 6, right? So 1, 2, 3, 4, 5, 6, right? So we're good between the 5 and the 6. Between the 1 and the 6, there's not an axial hydrogen, so we're cooked. So this is actually the only product we have here. Okay, now for this one, right, so here I'll try to this way. Right, so we have OH, so this is actually going to, I would probably list it as without the counter ion, right, so it'll be OH minus. Right, so for SN2, right, we always get, right, we're going to get a tack here to push that away, but when we do an SN2 reaction, we always get an inversion of stereochemistry, right, so there was a hydrogen behind here, right, didn't need to be shown. That gets pushed forward, right, and now the OH is behind, and then we're kicked off our bromide. Okay, so with that, so this is the product here. The OH, you have to be aware of the stereochemistry that for SN2, right, we get inversion of stereochemistry. Now for SN1, right, we get a racemic mixture, right? Right, because remember that first step is always the bromine leaving, right? And this ends up going flat. And so now the OH can come in here, right? And it can come in if it comes in from the front side, right? You would get that, right? Because there's a hydrogen back here, right? Or you could have it coming in from the back side, which would put the OH behind. Oop. H. Okay, so for here you're going to get two products. You're going to get both enantiomers. Okay? So there we go. So you're going to get one of these curved arrow mechanisms. Okay? So like that. So let's say we do we'll do this substrate, right? So we're going to do the SN1, SN2, E1, E2. But they all work the same way, okay? So for that, so for SN1, right? So for that, so right, I'm going to say Br OH minus, right, and then SN1, right, so you get OH coming forward and OH going behind, right? So show me the mechanism, right? So for the SN1, right, the first step is always this thing leaving, right? The leaving group leaving, right? So there's a hydrogen here, right? So that hydrogen remains and that goes flat, right? So plus the Br minus. So now this comes in and attacks either way, either from the forward or the back to give you that. Right, so it's going to be two steps. For an SN1 reaction, you get two steps, right? The leaving group leaving, and then the nucleophile coming in and attacking. Now for the SN2 reaction, right? Everything happens in one step, right? So the ones take two steps, the twos take one step. Okay? It's going to be this attacking at that carbon, and, right? And pushing the bromine away, and that's it. Happens all in one step. Oh, and then plus bromine, Br minus. Okay? Now for the E1 reaction, right? OH minus, right? So I should put that up there. So for the E1 reaction, right, it's very similar to this step here. First thing that happens, this goes away, right? So now you're left with, oh, I should have given you the product, right? There, right? So that goes away to leave the carbocation there. Now, instead, what happens is instead of the OH coming and attacking the carbocation, what it does is it actually comes in here, grabs one of those hydrogens, and those fall down there to give the fourth bond here. Notice this goes from 2 hydrogens to 1 hydrogen. That means this guy's reacted with that, and then plus water. HOH. Okay, so you need to make the double bond right here. So the excuse me, the base is going to react on this side, right? Because these are the two. This is where that double bond is going to be, right? So we need to rip off a hydrogen here. Those electrons collapse down to make the fourth bond for this carbon, right? So with that, to give this double bond here. Okay. The mechanism for the E2 mechanism is going to be very similar, but again, right? Just like this one, it happens all in one step. Right? You're still getting attack there, that falling down and that pushing away, right? But it's happening all in one step, just like this one here. So the one reactions happen in two steps. The two reactions, right? SN2, E2, they happen in one step. Go figure. Okay, so for this product, right, we're gonna have four different products. You need to be able to predict them and show the mechanism for how they work. Okay, they all work the same way. Okay, so you're gonna have this double bond attacking the HCl, right, and then give the two products from that, and then you're gonna have the other double bond coming in and attacking, and then giving the two products, right? So we're gonna say, okay, let's do these products, right? So for here, right? So that H is going to be, so that new H is going to be here, right? Leaving a carbocation there. You want that carbocation right next to that double bond, right? Because, right, you can make a resonance structure. So this double bond moves over there, which puts the carbocation there, right? We're skipping that one and going there, right? We also liberated a chlorine, right? And so if the chlorine sees that, it's going to attack there, right? To give this molecule. Right? If it sees this one, right, it's going to attack there. To see that molecule. Okay? So there's two of the molecules. Now, instead, what we're going to do is we're going to say, okay, what if instead this double bond attacked, right? What would you get? Right, so now, again, right, the hydrogen is going to go there, right, so that we could put the carbocation there, right? So it's right next to this double bond. Okay? So again, reason why, right? Because you can do a resonance structure to move that charge around. If it's here, it's too far away to get to that double bond, but if it's right there, you can get the resonance structure. Right? So that goes there, and so again, you get the skipping effect. You skip that one, and the carbocation ends up there. Right? This hydrogen's still there. But again, you liberated that chlorine, right, from here. Right? So now, again, if he sees this molecule, right, it'll attack there to give that. If you attacks there, right, to get that product, right? So here's your four products, okay? But it's always going to work the same way. One double bond attacks, kicks this away to make a carbocation, which then you get the resonance structure, and then the chlorine can attack either one. Now, you come back to this one. Now, that double bond, the other double bond attacks to give this carbocation, you get the resonance structure, and now the chlorine will attack either one to give here. And here are your four products, okay? Like that, but you do it the exact same way each time, no matter what the molecule looks like. Okay, so for the Diels-Alder, you're going to have, sort of predict the product kind of questions, right? So the mechanism is always going to look like this, right? So this goes there, that goes there, that goes there, right? And so CH3, CH3, right? So, and then HH, right? Right, so you have to pick. So for a regular diene like this, right, so you have to pick, right? So in this case, these guys are going up, right? So this side always goes one way, this side always goes the other, right? So that means these guys are down, which they're not shown here, but they would be like this, like that. Okay, the two methyl groups, they're on the same side of the dienophile, right? So they're going up. Here we go, right? So that means the other side is going down. Right? Now for here, right, I'm going to just redraw this. Right, we're going to say, let's say the CH2 that's here, it has to get out of the way, right? So we're going to say that's going up, okay? So when you do the mechanism here, right, so C, like that, okay? Again, you get this attacking there, right? That attacking there, and that pushing there, right? So the bond that you're making is this right here. Here is your cyclohexane, right? It just so happens to have something in the middle here that connects this carbon to that carbon, right? This carbon to that carbon. But the cyclohexane is the same. You're just looking at this molecule from the top, okay? Now the trick to this is that, let's assume that your CH2 is going up, okay? That would be the opposite. This is the opposite is true if the CH2 is going behind. But if the CH2 is up, what you have to do is you have to look to see on your dienophile, is there anything that has an extra set of pi bonds? Okay, so here it is right there. Right, here it is right there. Okay, so the rule goes, if this is going up, that means the thing with the pi bonds is going down. Okay, that means this whole side, right? Because this methyl group has to follow this guy's lead. So that means these guys are going down because this CH2 here, CH2 is going up. So if this side is going down, right, that means these two hydrogens here are going up. Okay, this sets the stereochemistry for all the four other sets, right? Because this is saying, okay, that's up, So that means this one's down, which means this one's down. Okay, because it's just like this side, right? This side was up, right? So here we're saying, well, now this side's down. That means this side has to go up. Okay, so the two hydrogens have to be going up like this, right? Which means this guy here, the aldehyde, and the methyl is going down, right? So down, down, right? There's also a hydrogen going up, hydrogen going up. Okay, this is just this molecule looking from the top, but it's a little bit easier to see. We got the hydrogen. Okay, so by that, so you're going to have one like this. You have to work it through. Okay, you sort of have on here. I included on the new set of slides, the updated slides. I included this this sort of explanation for you. So there you go. Now for the reactions to know, I'm going to do this a little bit differently. What I'm going to do is I'm going to show you an example of reaction, but I'm really going to tell you what it is here, right? So the SOCl2, right? What does that do? That converts this OH into a Cl, right? That's the important thing, right? This converts an OH into a Cl, no matter what it is. Okay. The PBr3, right? What does that do? It converts an OH into a Br, right? It converts an OH into a Br, OH into Br. This tosylate, right? This TosCl, right? What does that do? It converts an OH into an OTOS, and this is the tosylate here, right? TOS is fine, right? And then this is a fantastic leaving group. Its sole purpose in life is to leave, is to make sure, to get it to your group here so it's a good leaving group. Okay, so with that, so this is how you're going to start seeing these from now on. It's sort of reactions to know. It's going to be sort of a little bit more of an explanation as to what this needs, right? So this is probably the more important than this, but I wanted to show you an example of what the reaction is doing. Okay. Okay, so for this one, right, you're going to need this equation here, right? So NADH is a biological reducing agent. It's just a biological source of H-. Okay? Absorption at maximum of 340 nanometers. Okay, that's just sort of where it absorbs. Okay, the extinction coefficient, which is this, is the 6300. Okay, so extinction coefficient is that. Using a 1 centimeter cuvette, that's here. This is the path length, right? That's important because if your cuvette is twice as large, right, it's going through twice as much material, right? So that would cause that to be twice. You're going to absorb twice as much. So we have to take that into account. Okay, and then the absorbance is the A is 0.025. So that would be here, right? What's the concentration? So we're looking for this. Okay, so what's going to happen is I'm going to give you 3 of these. You got to figure out the 4th, right? So I'm going to give you that, say that, and that. You have to figure out this. If I give you these 3, right, you have to figure out what the absorption is, right? So it's just basic algebra, right? So here we go. So 0.025, right? So with that, the extinction coefficient is 6,300 molar per centimeter, right? Times the C, right? That's what we're looking for. Times 1 centimeter. Okay. Now notice what number we didn't put in here. We didn't use this number here. Right, that's just sort of an extra number, right? That's where we took the reading, but it doesn't actually factor into this equation. It just so happened that the reading was at here, stuff like that. But but this really doesn't matter. A lot of students try to throw that in there somewhere, and it throws off the calculation, right? This one here, the extinction coefficient, this is one of those things. It's just a constant for the molecule, stuff like that. So this is just experimentally figured out from the molecule. Like that. So here we go, right? So we can cancel out the centimeters here, right? So so if you just divide 6,300 per molar on both sides, right? 6,300 per molar, right? So C is equal to 0.025 divided by 6,300, right? Divided, something that pops the molar into the numerator. Okay, you put that into your calculator. It's 4.0 times 10 to the minus 6. Molar. If you want to be extra fancy, you could say 6 micromolar, because micro means times 10 to the minus 6. 4.0 times 10 to the minus 6 molar. Okay, I'll take either answer. I don't care. Stuff like that. So because these are technically both right. Stuff like that. So, but it's not going to be any more complicated than this. They're going to give you 3 of these. You got to figure out the 4th. stuff like that. So, but I will give you that equation, although just give it to you like this. You need to know how to use it. Stuff like that. So, okay. So for this one, right? So like that. So if it's aromatic or anti-aromatic, right? You need these Huckel numbers, right? Right. So it's 2, 6, 10, 14, 18, 22, on, right? So they're always by 4, right? And then I always start at the 6 because benzene we know is aromatic. That's sort of, that's the biggie. And then you go out by 4s either way. If you have this number of pi electrons, right? You have an aromatic. If it's not one of these numbers, then it's anti-aromatic. Not too hard. Okay. So look. So here we go. So we're going to look at this one, right? So just red, right? So how many pi electrons do we have? Well, we have 2 here, right, and 2 here. So we have 4. That's not one of our Huckel numbers, right? So this is anti-aromatic. Okay. So what do we have here, right? We have 2, 2, and 2, right? So you add them up. That's 6. Oh, here we go. This is benzene, so it better be. So this is aromatic. Right, so here we go here, right? So 2, 4, is it 2, 2, 2, 2, right? So this would be 8, right? So this would be anti-aromatic. Okay. Now, if you came in here and you said, okay, well, what about this? So how do we deal with lone pairs? Well, if you have a heterocycle like this, which means it has a nitrogen, a sulfur, oxygen in it, right? Things with lone pairs. Basically, what it's going to do is it's going to move these around so that it'll give you one of these Huckel numbers. So in this case, right? So here's 2, here's 2, here's. We're going to use those that lone pair. So we're going to move that 2. It's 6, so it's aromatic. Right? Now, if I gave you something like this. Well, you say, well, there's 2 here, there's 2 here, and there's 2 here, right? Oh, we had the lone pair here, which we used here, right? So that should be 8. Well, it gets a little more complicated than that. What it does, what the molecule does, it actually gets these off. It sort of basically hides them. And so what it does is it puts those 90 degrees away from these guys here, so it's almost like it's hiding them. So really, it has 6 electrons, so it's aromatic. 99.9% of the time, if you have a ring like this, where everything has a p orbital, and you have a heterocycle in there, 99.9 times out of 100, it's going to be aromatic. Okay, so it's going to do what it needs to do to make give itself one of these Huckel numbers, because there's so much stability involved in becoming aromatic that it's going to do whatever it needs to do. Now, if there's a charge. Okay, so I'm going to. So let's say that has a positive charge onto it. Okay. Well, these all have p orbitals to it here, but again, you have 2, 2, 2, maybe 6, right? So this is aromatic. It doesn't matter that this is a positive charge, right? That just means it has a pi electron with it. Right, it has a p orbital that can participate in this. So that's aromatic. If you had something like this, like that, right? Now, once again, you have 2, 4, 6, right? So now, right, we can get to the Huckel. So it's going to put that in there, right? So we can get to that Huckel number if we put that in. So again, this is aromatic. Right? It doesn't have to be, but it is, because we can get to that. So be careful, stuff like that. So heterocycles basically always going to be aromatic. Charges, you just do it like you would do up here with these guys there, stuff like that. Not too bad. So okay, so for these, okay, there are naming compounds. Okay, so for these. There's in the start of chapter 15, there were six base structures you needed to know, right? So you needed CH3. This is toluene. This is with the ketone. This is acetophenone. Right? If it's a nitrogen, this is aniline. OH is phenol. What was the other one? This one here is an aldehyde group. This was actually abbreviated CHO. That stands for aldehyde. That's abbreviation for aldehyde. So this is benzaldehyde. And then this one here, carboxylic acid. So this is benzoic acid. Okay. So about that. So these are the 16. There's also xylene, which is actually 2 methyl groups. And then there's styrene, which is a double bond hanging off of here. So don't worry about those two. Toluene has just one methyl group hanging off. It's more than one, and then we just revert back to the benzene. But the first thing you got to do is you have to say, okay, is there one of these groups on here? Okay, and in this case there is, right? So there's this, right? So here's this phenol group. Okay, so our base structure is going to be phenol. Okay, and so like that, and so right, so that's nice because the numbering is, this is going to start off as 1, right? So with that, so that means that we have this one, this single side chain here, which would be chloro, right? So usually it's good to go clockwise, counterclockwise. We know the phenol, the base structure, wherever that thing is attached with the group that makes it, the base structure is attached, that's going to be carbon 1. So if we go clockwise, it'd be 1, 2, 3, 4, 5, 6, right? So it'd be 3. If we did this counterclockwise, right, it'd be 1, 2, 3, 4, 5, 6, right? So it'd be at 5, right? Since this is the lower number, we're going to take that. So it becomes 3-chlorophenol. Okay. So for here, notice that, you know, having a chlorine, and this is a nitro group. So with that, so there's no base structure here. So when there's no base structure, then we just say this is benzene. Okay, so we have that guy and that guy, right? So we have a chloro and a nitro. I'm not going to give you I'm not going to give you nitro on the test, but that's just one to know. We talked about that in the notes a little bit, but I'm not going to throw that at you. But just like the cyclohexanes, right? So we're going to say, okay, where a side chain is attached on the ring, right? We're going to say that that's number 1. So let's say this is 1, right? And then we cycle around clockwise, counterclockwise towards its nearest side chain neighbor, which would be here. So 2, 3, 4, 5, 6, right? So 2, 1, 3. But if we said, okay, this is 1, then we would go 1, 2, 3, 4, 5, 6, right? So towards the nearest neighbor, side chain neighbor, right? So this would be 1 and 3, right? So there's a tie, right? So just like the cyclohexane, we say, okay, the one that's first alphabetically, so in this case it's chloro, that gets the 1. So we're going to use this numbering. So it becomes 1 chloro, 3 nitro, benzene. Okay. Now, if you had something like this, I don't know, NH2, CH3, right? Now there are 2 base structures. There's this one here, and then there's this one here. And so now you have to apply priority groups, right? So there's this one here, this is aniline, right? And this one is toluene. Okay, so you have the rules, and basically everything is a higher priority than toluene, right? So with that, so we're going to say, we're going to say, okay, our base structure is going to be aniline, right? And then we're just going to take this as a methyl group, right? Right. So we're going to go, right. So we're going to set that as number 1 because that's our aniline, right? Clockwise towards our nearest neighbor, right? So it'd be 3. So it becomes 3-methyl aniline. That. Okay. Now, the other thing that could happen is, let's say you have a big chain hanging off of here, 2, 4, 6, 8, right? So with that, and then let's say you have something like this, right? So remember with the right? So with the rings, you know, so this is 6-membered ring, right? And this is 1, 2, 3, 4, 5, 6, 7, 8. Since this is longer, actually the structure, the main chain actually ends up being the straight chain because it's longer. It has more carbons in it than the ring. Okay, so this is 8, so C8. So this would be octane. Okay, now a benzene side chain is actually called phenyl. Okay, you would think it would be benzyl, right? Because that makes sense, right? Side chain is a YL. You just take off the suffix and add YL to it. Well, it turns out this is a benzyl. There's a CH2 coming into that main chain. It's attached through a CH2. Okay, so this is actually a benzyl. Right, so this would be the main chain, right? But a benzyl it's connected through a CH2. It's actually connected through basically like a toluene. So that turns out the history of this is that this was discovered before this one, so they named this first. They named it before they knew what was going on. So they named it, since this was already taken, they switched to phenyl. Right, so and they just never got around to changing it back. Stuff like that. So, okay. So you just have to struggle through it. Okay, so just a benzene ring, right, is called a phenyl group, right? So we need to figure out the numbering, right? So it'd be, if we said this was number 1, it'd be 1, 2, 3, 4, 5, 6, 7, 8, right? So it'd be hanging off at carbon 3. But if we did red numbering, right, it'd be 1, 2, 3, 4, 5, 6, 7, 8, right? So it'd be hanging off of carbon 6, right? So we're going to take the 3, right? So this is going to be 3 phenyl octane. There you go. So that's the naming.